session. So feel free to switch off your cameras if you need. And we're very happy to present you to Nora Molkenthin, who's researcher from Potsdam Climate Institute, very known also institute now, and it's a very big pleasure, particularly for us, to welcome her, because her work also has been quite original and very kind of finding new ways and developing interdisciplinary methods in research on mobility and climate. She has done a lot of research on that. So I'm really happy, and without further ado, Nora, you're the presenter now.
Yeah, thank you very much for that kind introduction. And sorry for the technical difficulties. So yeah, I will today present some of my group's work on on-demand ride pooling as a statistical physics problem. And well, the problem is pretty easily stated, but not so easily solved. So the idea is that say you have a city or a region, and you have some people or also goods that have a need to travel somewhere else. Now, the sort of standard option is that each of them travels on their own, and that requires a lot of traffic and a lot of cars and a lot of fuel and so on. And so a lot could be saved by just bundling some of these rides together, and that's exactly what this ride pooling is all about. You just take a few trips that go in a similar direction, and you do them with the same car. So in this case, for example, here we have 5 trips, and then we do them with 2 cars in the bundled version. Now, does that solve all of our problems? Well, I mean, probably not all of them, but potentially it could mitigate at least some of our very pressing issues that we're currently facing. So, I mean, apart from reducing CO2 emissions, if you can bundle together some trips, you can also reduce other pollutions, say air pollution by the cars, or noise pollution, and so on. But you can also reduce jamming, so you could not only make travel safer and cleaner, but also faster. Although maybe that makes it more dangerous again. Who knows? But you know, you win some, you lose some. Then, if you have a functioning ride pooling service, maybe fewer people will feel the need to own a car. So you can also potentially reduce the amount of space taken up by ugly car parks, and maybe replace them by something nice, like a park or a social housing or a playground or something. Now, moving away from cars, such a service could also complement public transport if done right. I mean, it could also take away customers from public transport if set up in the wrong way, potentially. And then, say, if a train line fails, you can instead take ride pooling, and everything becomes a little bit more flexible and a little bit less error prone, or less prone to like one individual error. On top of that, if you have a rural area, often what you see is that you have very infrequent buses or no buses at all. And then if you do find a bus that goes vaguely in your direction, it turns out there's only 3 other people on the bus. So it's also highly, not very profitable. And so if set up in the right way, one would hope that such a ride-sharing service could address all of those problems at once. However, what is the right way to do things? Obviously, you can do things experimentally, but I'm not an experimentalist. I'm very much a theoretician. And B, if you set, it's very hard to control all of the parameters, because if you want to work with the real world. So what you end up with is a lot of very contradictory stories and studies and papers. So now we're going at it from the perspective of theoreticians. So to do this, first of all, we phrase the system as in mathematical terms. So we go from streets to networks. I mean, this is not a representation that is unambiguous. In fact, there's a lot of ambiguity in here, but it doesn't matter for now. Let's assume that all the street corners are nodes, and all the streets are represented by edges. Then we have write requests, which in principle are complex beings, but we just represent them by random node pairs, and they follow a certain request pattern in space and a frequency in time. For most of this talk, this frequency will just be it's just a Poisson process, so it just has one frequency. But I mean, in principle, it could also fluctuate over time or be drawn from other distributions than the Poisson distribution. The next thing to represent are the vehicles, the buses, and those we represent by stop lists. That's just a list of subsequent nodes that this vehicle is stopping at. And so this is a sort of a list of lists. And there, I mean, the system parameters would be the number of vehicles that you have in the system, the speed at which they go. And then also there's a mystery ingredient to our whole system, which is the request distribution algorithm that decides which customer goes into which stop list at which precise point. Now, this last point is that a lot of them have been proposed. There's no shortage, but they do all share in common some features, and we will just use a very simple one. And here I will explain which one. So the dispatching algorithm that we're using is one that minimizes the arrival time of the new passenger without causing delays to the already booked passengers. So what this means is, so we suppose you have a set of those stop lists. Now a new pair of nodes come, a new desired trip comes in the form of a pair of pickup and drop-off nodes. And we take out one of those stop lists, and then we check if the pickup node is anywhere on this route. So in this example, the pickup node is like it's a 5 by 5 grid. So the pickup node is 2, 2. So that is already a stop. So the other 2, 2 will just join this one. And then we check if the drop-off node is also anywhere on the route, which means it's either the node is already in the set of nodes, or it's somewhere on a shortest path. In this case, the answer to this is no. So what do? We add it to the end. Now, had the pickup.
Sorry, Nora, just a question for clarification. Sorry, but you always have pickup nodes in coordinates, kind of like XY coordinates? Because
no, I mean, you could also just name the nodes.
Okay, so it's just for this.
This is just an illustrative example.
Mm-hmm. Thanks.
So where was I? Yeah, so had this first node not been somewhere on the route, they would have just both been attached to the end. And then you do this for every one of the vehicles that are servicing your system, and you select the one where the drop-off time is the earliest. So you check for each of these buses when would the person be delivered to their desired location, and you just pick the one where it's the earliest. So that way, nobody gets delayed from the previous passengers, because you only insert things inside the stop list if they don't cause a diversion, and then you add stuff to the end. So what this means is that you will always sort of you will always know upfront how much of a delay it causes. It might cause you a delay. You might go through the whole network like on a night bus, because you got attached to the end, but at least you have certainty. So what sort of dynamics does this cause? If you imagine you first have a system where there's no queue, like all the vehicles are empty, then you will just get the closest vehicle to you that comes, picks you up, and brings you to your location. But therefore, the probability that you get attached to the end of the queue is very, very high. So you will always make the queue longer. Whereas if you get inserted in the middle, if you are in a state of the system where the buses like cover the whole network, it's very likely that you're already on the route. So the whole route will not get longer. That doesn't mean you don't take ages to get where you want to, but it does mean that eventually an equilibrium will be reached. And the equilibrium is between what the bus services at the beginning, because it drives at a constant speed, and what is attached to the end of the route, because that depends on how long the route already is. You can see this in two examples here. So this is an example with only one vehicle. Therefore, the filling up time is very, very fast. So in the beginning, it all starts at 0, then it very steeply rises, and then it ends at, in this depending on the system load. Here it's around 35. Here it ends at like 15, and here it's at like around 1 or something. If you have several vehicles, this rise happens on average a bit slower, but you see the same thing. So for a while it rises, and then it settles at a certain average. And that's this equilibrium state that we're talking about. So we will only talk about this equilibrium state in the following. And now I already used the term load. What we call load is the normalized load, which consists of the request frequency normalized by the average shortest path length on the network, which is called angular brackets L, and it's divided by the number of vehicles B, and the velocity of those vehicles, which we pretty much always set to 1. Okay, so that's our equilibrium. Now the question is, where is that equilibrium? Like how long is our queue of scheduled customers?
And if I may, Nora, in the previous slide, just for understanding, because maybe I'm sorry I'm slow. In the previous slide where you were showing the equilibrium, what is, talking about the equilibrium in the previous one, in the first slide, in the first picture on the left, right, here, N here corresponds to number of...
Okay. N is the number of stops in the stop list. C is the number of customers in the stop list. So N, they're both essentially the same thing. N just means that you're counting those customers twice that haven't been picked up yet, and those customers once that are already on the bus, that have already been picked up. And in C, you just count everyone once. We also have another measure that is also equivalent for all intents and purposes, which we call O, which is the occupancy, which is how many people are currently on the vehicle. That only becomes important if your vehicle is realistic enough to only have a certain capacity of seats. I will speak about this a little bit later, but essentially, for all dynamic purposes, they can be treated as equivalent, which is why I brushed over this quickly. It also appears in a future slide. So in this work, we work with the value C, just because some of the math looks nicer that way, because you don't have a factor 2 in some in one place. So what you see is that as you increase the load, which is the so you increase the number of requests that come in per vehicle. So since we increase we keep the number of vehicles the same, but we increase the load. So you just get more and more requests. And you can see that the more requests you have, the longer the queue. But how steeply the queue length increases, it depends strongly on what type of graph your system is operating on. So for very simple graphs, like the minimal graph or the ring, or just very small graphs, it rises more slowly. And for more complex graphs or more branchy graphs, where you can imagine that it's very hard to find partners to share a ride with, this goes more steeply. And similarly, the more vehicles you have, the fewer vehicles you have, the harder it is to share. The longer you have to wait to find something that is shareable. Whereas if you have many vehicles, then almost every direction at almost every time there's going to be a vehicle that's already going. And here it comes because this is a normalized X, this means this curve just in general, in total, has a lot more requests than this curve. So it's just everything's a lot denser. This is very much a sort of a thermodynamic limit. And you can also see that maybe you can see that, it's kind of hard to see. There's a dotted line here at the bottom of both of these graphs. This is the sort of absolute best that you can hope for, and the sort of minimum slope that is even possible, because this is the slope that you get if you assume that everybody finds a vehicle that's basically right next to them, wherever they post their request from, that drives them straight to their desired location. So they have zero waiting time, and they just drive straight to where they want to go. You can't be any faster than that without breaking the speed limit of the city. Now, as we've seen, all those nice linear slopes, we now describe the system efficiency by its slope. And since the slope approaches this this particular slope of exactly 1, we take the inverse, because then an efficiency of 1 is the best that you can reach. And before that, you have efficiencies that are between 0 and 1, which is nice if you want to call something an efficiency. So for smaller numbers of buses, the system is less efficient. And then as you increase the number of vehicles, no matter what your topology, you always approach the efficiency of 1. So the good news is you can always get perfect service, but you need more vehicles on a larger, more complicated network. And what we also observe is that all of these curves look kind of similar, even though they are on very different graphs. And it looks like there should just be a factor that collapses them. And this is true. And we call this the topological factor, which is something that characterizes the sort of ride-sharing propensity of a topology. And this works very nicely for the artificial networks, but it also sort of works for these networks that we extracted from actual street networks. It's just that at low numbers of buses, the collapse is not so great. Now, how can we approach this analytically? We can express this number of people in the queue by the total length of time they spend waiting to get to their desired location, which consists of the sum simply of the time they wait and the time they drive. And then you divide this by the average time it takes in between two requests going to the same bus. So that for one single bus, you would have requests that are assigned to this bus sequentially, and the average time between two consecutive requests being placed in that bus's stop list is a sort of is 1 over lambda, which is the request frequency. So now we just have to find an estimate for the waiting time and driving time, and that's not so easy analytically. But if we look at the simulations, we find that the driving time very sort of soon approaches the average shortest path length, which is what the stabilizer said, whereas the waiting time goes down to 0 as a sort of 1 over b, as like a power law for the number of vehicles. And if you just insert all this in the previously shown equation, then you find this equation, which fits the curves very nicely. And now we come to the capacity, and so that we say that the occupancy of these vehicles at each time can never exceed some number, because that's the number of seats the bus has, or the number of people that you can squeeze into it. And here we find that initially, yeah, this mapping doesn't look so good anymore, depending on how much you go above the, or like how close you get to the limit of the system in terms of what the system can deliver. However, you can regain the scaling by accounting for the delay you get from some vehicles not being available. So you just at each so for a particular capacity and a particular load, you can compute how many vehicles would be full, and then you just take those out of the equation, and then you just get higher you just have sort of effectively fewer vehicles, and therefore instead of working with the vehicle with the actual number of vehicles, you just work with the effective number of vehicles that are actually free and can service your request at this time. Okay, so that's one nice mapping that we do from the normal from the vanilla case to a slightly more complicated case, and now we want to go in a slightly different direction, which is we want to vary the request distribution in space. So rather than just having a uniform distribution where as many requests come from all of the nodes, we now have a very non-uniform distribution, which is binary. And so you have the orange nodes from which requests are placed and the green nodes from which no requests are placed. So these orange nodes just have a lot of requests and the rest has nothing. So ideally what we would want is we want to have one structure that that sort of reduces this to the previous problem. So we want to find a network on which this is a uniform distribution, and we get the same outcome in terms of routes that are being driven on this network. And to do this, let's just take all the green nodes out, and let's just connect all the pairs of red nodes by a, I don't know how well visible that is, all the pairs of red nodes by a link of the length that you would, there was the distance on the original network. So in this case, between this node and this node, now I went to the next slide. Between this node and this node, the distance is 1, 2, 3, 4, 5. So we connect them with a link of length 5. And the and so on. We do this for the whole network, and we just make a complete graph out of this. And if we simulate this, we find that it matches perfectly. We basically haven't lost any information. Now, if we look at what this is absolutely not surprising if we look at what the dispatcher algorithm does, because the dispatcher algorithm just looks at the distances, like basically the distance matrix between any pair of nodes. And this means we can actually reduce it further, because we can take out any of those links, the removal of which doesn't change the distance matrix. For example, the distance between this node and this node is 5 along the direct route, but if you go via this node, you go 3 and then 2. So in total, that's also 5. So you can just as well lose this link. The same is true for this link and this link. However, this one you can't lose because the length is 3 and the length between the length here is 2 and there it's 3. So that would be a length of 5. So you have to keep that one. So then we arrive at this, which we call the minimal effective topology. And it turns out this also has the same slope, and also typically given the same request, a series of requests, it should also have the same stop list. Now, does this work for multiple vehicles? The answer is yes. Does this work for another request distribution, like dispatcher algorithm? Yes, because here that's why this curve is so round. Here we're not inserting everything. We're assuming that the customers only have a finite patience. So these weird customers don't want to wait for 3 days for the vehicle to bring to pick them up. They have a limit at which point they say, no, I'm okay. I'll ask my mom to drive me. But still the minimal effective topology persists and works, which is nice. So we found a mapping to a much simpler system for the binary request distribution. Now the question is, can you see that the question that we came that appeared to us after this was can you see this in the link usage? Can you see that some links in this complete request graph, for example, are used more than others, like those that don't appear again in the minimal effective topology? Are they just not utilized ever? And here we actually found something very interesting and surprising, because if you assume, so our initial guess was that if you assume all the links in the minimal effective topology are driven across with equal probability, then you can reproduce the result you get from the simulations for link usage, where you just measure which links get driven on. However, that is not the case. You get something wrong. And what we observed is that it's in the simulated result, you get a lot more link usage here on the outskirts, like on this outer line, and less on the in the inside. Then we found what probably happens is that the vehicle goes around in circles. And there are 4 options for these circles that are basically like Hamiltonian cycles on those 5 links, on those 5 nodes. And so this is basically a superposition of those 4 cycles. So does that mean what actually happens is that if the request rate is high enough, if the load on the system is high enough, you get bus service. I mean, this looks very much like a line service establishing. And yeah, that is a question that we haven't really answered yet. And now I'm coming to a slightly different question, and that is, why look at binary request distributions? That's not something that we will ever see in nature or in a city. Things don't tend to be binary. Well, they're not binary if they just come up by themselves, but they're binary if we make them, or they're similar to binary. So suppose you have the following situation. You have this network, and you have one bus that can service this network, and then you have all these people who want to get on it. So in the ride-sharing spirit, what would happen is the bus would go to the black guy, and then it would go to the red guy, then it would go to the green guy, and then it would go to the purple guy, and then it would go to the blue guy. But it would, like, the blue guy would have to wait for a really long time. Now, what if instead, while waiting, these people just walk one street corner? Then the bus only would have to go here, and then from there it would have to go back here, and basically it could just, I mean, I think I'm a bit mean to the purple guy. Maybe you should go here and then there. But in any case, you could reduce the amount of detour for everyone by requiring everyone to walk just a little bit. And this is basically something that we phrase in terms of establishing some super nodes that just have one central node that you always have to walk to. And we look at what is the optimal size and shape and location of those super nodes. And we do this using Markov chain Monte Carlo simulations by starting from an initial network when nobody ever has to walk. And then we make a proposal by randomly merging 2 adjacent supernodes to form a larger supernode, or by splitting one supernode, if possible, into 2 smaller supernodes. And after this proposal has been placed, we run a simulation and we compute what's the average time that a passenger takes to travel to their destination. And what we find when we do this is, well, depending on the temperature that we're using, where the temperature means the probability of accepting some like a proposal step, even if it's not beneficial. If it's beneficial, it's always accepted. But in order to find not only a local minimum but a global minimum, sometimes you have to maybe go in the wrong direction, and that way you find an ensemble of solutions that are pretty good, but not maybe the lowest energy.
Nora, you have 3 minutes. Do you have time?
Okay.
So that we can also discuss more. Feel free.
No, it's fine.
Hurry.
So what you end up with is you find that the supernodes that people walk to tend to be on street corners, which is not surprising. We also find that if you walk if everyone is assumed to walk faster, or rather, say the system is jammed and everybody's driving slower, you get larger supernodes and smaller routes for the vehicle. It also works on actual road networks. You can also kind of see in those examples that it would be reasonable to assume that the vehicle is going in a cycle. I think that's the main point I wanted to get to. So here, the vehicle would be going in a very small cycle, for example, whereas people would walk to that cycle, then drive a little bit and walk away from that cycle again. Here, this also looks very cyclic, but I mean, that's partially because of how we selected the region. And so well-connected, evenly distributed hubs remain. Faster walking means that you remain fewer nodes. And it's consistent with assuming that the vehicle goes in cycles. And we can even use the cycle for estimating the travel time without having to run the simulation. And now I would like to, summarize that we posed on-demand ride pooling as a statistical physics problem. We found a universal scaling law with the number of vehicles, which applies across different topologies for different request distribution and even for different insertion algorithms. And at high demand, we have some evidence that cyclic routes form. And from this, we derive some outlook. Here are some of my favorite further questions. So what do those cycles look like, especially for multiple vehicles? Do they intersect? Are they complementary? Are there like just one cycle that covers the whole network, but several of them overlapping? Do they coexist with non-cyclic ride pooling vehicles? Are there some vehicles that just go in a cycle and others that bring random people to random places? And is there a transition between the phases? Can you see this as a phase transition? And ultimately, so that sort of the practical question that you could try to get to with this is, can we find an optimal line service for a system by just using some MCMC like this and finding the cyclic routes? If that would be possible, that would be super cool. And with this, I want to thank you for your attention. These are the papers and theses that this is this talk was based on. Thanks to my collaborators from those projects, and I welcome your questions if we still have time for those.
Yes, I do have some questions, unless some other people want to start. Or maybe I can start right now. I will actually stop recording.